Hello and welcome to this video on the orthogonal projection of a vector onto a subspace, and this is a subspace of an inner product space. I'm hoping that before this you've seen my video on the orthogonal projection of one vector onto another vector, because the formula for that concept's going to come back in a big way in this video. And how I'm going to start this off is just with a refresher on orthogonal complements. What is the orthogonal complement of a subspace? And some results related to orthogonal complements. And how a vector space, an inner product space, can be expressed as a direct sum of a subspace and its orthogonal complement. Right, just going to refresh your memory on those. Then I'll talk about, the title of the video, the orthogonal projection of a vector onto a subspace, and then also how do we find the orthogonal decomposition of a vector. That is just simply breaking up a vector, rewriting a vector as a sum of two orthogonal vectors. And then I'll go into several examples. I'll finish with like 3 examples at the end of the video in Euclidean space in R2 and R3, so I can actually show you some pictures. And the inner product will be the dot product, so that way orthogonality and perpendicularity mean the same thing. It'd be easier to envision orthogonal vectors when we talk about using the dot product as the inner product. But just know that the dot product doesn't always have to be the inner product, right? The inner product could be defined in some other way. But all these definitions I'm going to throw at you here are going to be useful in any example that you come across, whether or not the dot product is the inner product, right? So pay attention to how the inner product is defined, of course. And I say that every video involving orthogonality. Right, pay attention to how the inner product is defined. In this video, like I said, I'm only going to be using the dot product as the inner product, but just know that it could be defined in some other way on some other inner product spaces. Okay, so the beginning of this video, I'm going to just, I've had these pages up in previous videos before. Just a refresher as to what is the orthogonal complement of a subspace. Alright, so if W is a subspace of an inner product space V, the orthogonal complement of W, denoted by this W with the orthogonal symbol as a superscript, this is the orthogonal complement of W, is the set of all vectors in V that are orthogonal to every vector in W. Right, and symbolically this was put this way, right? The orthogonal complement of W is all the vectors V in V, such that the inner product of V with W is 0 for all vectors in W, right? All vectors W and W. Right. And something nice about this orthogonal complement of a subspace, it is also a subspace, and again this is a page I've had up in a previous video. The orthogonal complement of a vector of a subspace W is also a subspace of V. It's non-empty, 0 would be in there, it'd be closed under addition and closed under scalar multiplication. Okay, so we know that the orthogonal complement of a subspace is a subspace itself. Is also a vector space. And then another page I've shown in previous videos is that now that we have a subspace and its orthogonal complement, the larger inner product space V, that those were subspaces of, V, can be expressed as the sum, and in fact a direct sum, which we'll see in a minute, of W and its orthogonal complement, right? So V is equivalent to the sum of any subspace of V plus that subspace's orthogonal complement. Now what this means is that every vector in V can be expressed as a sum of a vector in W and a vector in the orthogonal complement of W. Right. And in fact, it can be expressed uniquely as a sum of vectors like this. The reason being is because, not only is V the sum of a subspace and its orthogonal complement, but any subspace intersected with its orthogonal complement will only contain the zero vector, right? They only share the zero vector. They have nothing else in common. And putting these two together, right? The fact that V is the sum of a subspace and its orthogonal complement, and that the intersection of a subspace and its orthogonal complement is only the zero vector, we would then say that V is a direct sum of W and its orthogonal complement. Remember, that was that little plus sign with the circle around it. And again, I put up a previous video on sums and direct sums of subspaces. So V is the direct sum of W and the orthogonal complement of W, meaning, this is a huge thing here, meaning that every vector in V can be expressed uniquely in only one way as a sum of a vector in W and a vector in the orthogonal complement of W. Alright, and that's huge. Right? And I can write any vector in the inner product space as a vector from W plus some vector from the orthogonal complement of W, and that's the only way I'd be able to do it. Alright, there'd be no other way to express it, right, uniquely. Alright, so keeping that in mind, now the question is, how do we do this? How do I take a vector from an inner product space and write it as a vector from some subspace W plus some vector from the orthogonal complement? And that's what the today's video is about. How we do this, how we decompose a vector from V into the sum of two orthogonal vectors, a vector from W and a vector from its orthogonal complement. Alright, so first I'll talk about how do we find this vector from W that I can break up, the vector from W component of vector V, right? And that would be the orthogonal projection onto that subspace, onto W. Right. So here's my first page, my first new page. This hasn't been in any previous videos. So what is the orthogonal projection of a vector onto a subspace? So suppose we're given a vector, say vector Y or V, whatever you want to call it. I'm calling it Y here. Given a vector Y from some inner product space V, remember I'm going to try to break this up into the sum of a vector from a subspace W plus a vector from its orthogonal complement. So we're given a vector Y from an inner product space V and some subspace W of V. Right? The orthogonal projection of Y onto W, denoted either by, this, you see how this was similar to, remember I had a video again up earlier of projecting a vector onto another vector. This is similar notation, but instead of the subscript here being a vector, it's a subspace. It's the projection of Y onto W. Very often, though, this is shortened in some books as just Y hat. Right? Y hat. Now, again, you're going to have to understand what this means depending on what kind of textbook you're in. Y hat means something different in a linear algebra book than it does in a statistics book, for instance. All right, so just be careful. But it's the projection of Y onto W. It is the sum of the vector projections. Remember again, I've mentioned I put up a video on projecting a vector onto another vector. Y hat here, or the projection of Y into W, is the sum of the vector projections of Y onto each vector in an orthogonal basis of W, and those are the key words there. or an orthogonal basis of W. Alright, so in order to find this vector projection of y onto subspace W, I need to know an orthogonal basis of W, and then project y onto each vector in that basis and add them up. Right, it's the sum of those vector projections. Okay, and I've written that out more symbolically on this next page. Right, so if, say, set B here has vectors u1, u2 through uk, if this set B is an orthogonal basis of W, then the projection, or the orthogonal projection of y onto W, or this y hat, is the projection of y onto u1 plus the projection of y onto u2 plus the projection of y onto u3 plus the projection of y onto uk. It's the sum of the projections of y onto each of these orthogonal basis vectors. And if you recall, again from an earlier video, the formula for the projection, how do you find the projection of one vector onto another? It just involved a lot of inner products. So the projection of y onto u1, remember it was the inner product of y with u1 divided by the inner product of u1 with itself times u1. Again, notice that the vector you're projecting onto shows up a lot. Shows up 4 times in this little formula. And the projection, and again I'm just replacing u1 with u2 with uk in all these. The projection of y onto u2 would be the inner product of y with u2 divided by the inner product of u2 with itself, times the vector u2, plus plus the projection of y into uk, same thing just with uk's everywhere. And the sum of all these projections will give me the what's called again the orthogonal projection of y onto W. And another way to think about this is the vector in W that is the closest to y. Alright, I'll write that out in words here. The y hat y hat is the vector in W is the vector in the subspace W that is closest to vector y. Right, and that's not y hat, that's just vector y. In other words, the distance between y hat and y is a minimum for any vector in W. If you took the distance between y and any other vector in W, this would be less than or equal to that. This would be shorter. All right. So this is going to give me the vector in W that's closest to y. All right, that's what y hat is. All right. But the key is finding an orthogonal basis to the subspace, which you know how to do using the Schmidt process. I've only got one example at the end where I'm going to use the Schmidt process, but the key is if I'm given a subspace, I need to find an orthogonal basis to that subspace in order to then create a projection, right, a projection of a vector onto that subspace. Alright, so this will give me that vector in W, and then I'll need to find a vector in the orthogonal complement of W to complete what's called the decomposition of a vector, the orthogonal decomposition. So one more definition page here, and then I'll get into some examples. So the orthogonal decomposition, you're basically taking a vector and writing it and breaking it up into two pieces, two orthogonal pieces. The orthogonal decomposition of a vector y in an inner product space V is y equals y hat, which was that projection onto W, plus some vector z, Right? You can call this other vector z whatever you want. Just know that this other vector is in the orthogonal complement of w, right? Where y hat is in w. Right? It's that projection vector, the projection of y onto w. And z is in the orthogonal complement of w. And the way to find it is we're just going to take y minus y hat, okay, once you've found y hat. And here's a little generic picture. Right? If I have vector y in my vectors, if vector y is in V, you're going to project that down to W. So say this here is the vector y hat that's in W, and then you would add to that some orthogonal vector in the orthogonal complement of W, this vector z, so that the sum of them is y. And because an inner product space is a direct sum of a subspace and its orthogonal complement, the way that you write this will be unique. There won't be any other way to express y as a vector from W plus a vector from the orthogonal complement of W. This whatever decomposition you find will be the only way to do it. Right. Okay. So now for some examples, and again I'm only doing examples in R2 and R3 using the dot product as the inner product. Just please know that you might come across other examples where the vector spaces might be non-Euclidean, and the inner product might not be the dot product. You just got to pay attention. All right. I'm just using Euclidean space R2 and R3 here, and the dot product, so we can see when vectors are orthogonal, right? And that when you're talking about the dot product, vectors are orthogonal when they look like they're perpendicular, when they're perpendicular, right? So we can more easily visualize that. All right. So my first example. So I have a subspace. All right. So W is the span of the vector 3, 4. Remember what the span of 3, 4 would just be all the linear combinations of 3, 4, but there's only one vector 3, 4. So all the linear combinations of 3, 4 would just be the scalar multiples of 3, 4. So W is the span of 3, 4, all the scalar multiples of 3, 4, which would be represented by a line, right, going through the origin in R2. This is a subspace of R2. And the inner product we're going to use is the dot product, right? I'm saying under the dot product here. All right. So suppose we're given, just any vector in R2, any vector at all, and I've picked 0, 6 here. Right? You can take any vector you want from R2. What I'm going to do is take this vector 0, 6 from R2. And first I'm going to find its orthogonal projection onto W. Find the orthogonal projection of y onto W, right, which was called that y hat, or the proj projection of y onto W, either one. Alright, so in order to do that, the first thing I need, if I'm projecting onto W, the first thing I need is an orthogonal basis for W. So first, find an orthogonal basis, keyword being orthogonal. Alright, so here's a basis for W. It's pretty obvious the way I've written it, right? W is the span of just this set with a single vector. So a basis for W that I can very easily see right now is the set with the vector 3, 4. Right? It obviously spans W, and it's a single vector. Right? It's a set with a single vector, so definitely independent. And any set with a single vector you could consider orthogonal, kind of vacuously, because remember, an orthogonal set of vectors was one in which every pair of different vectors was orthogonal. Well, there are no different vectors in here, so we could consider this, vacuously an orthogonal basis. All right. So I'll write that off to the side. Any set with one vector can be considered an orthogonal basis. So any set with a single vector can be considered orthogonal. Right, even though there's really nothing to check, right? There's no pair of vectors to take the inner product of and see if it's 0. Alright, so this is good enough. Alright, this is good enough. So here it is. I'm asking, I want to find an orthogonal basis for W. Here it is, this set with the vector 3, 4. Alright. So I'm going to call this, I had up earlier, the orthogonal basis had these U vectors in it. So I'm going to call this vector 3, 4. I'm going to call this vector U1. Right, that's vector U1. So Y hat. Right, so this orthogonal projection, remember the formula from earlier, remember the orthogonal projection of a vector onto a subspace with a certain orthogonal basis was just the sum of the projections of that vector onto each basis vector. So Y hat here is going to be the projection of Y onto U1, and that's it, because there aren't any other vectors in this orthogonal basis, right? If there were more, then I'd be adding more projections. And what is this projection? Well, remember the projection is, this would be the inner product of Y with U1 divided by the inner product of U1 with itself times the vector U1. All right. So remember the inner product here is the dot product. So the numerator, right, what is the dot product of Y and U1? That's 0, 6, and 3, 4. Alright, well that's just, 0 times 3 is 0, plus 6 times 4 is 24, so the numerator is 24. And the denominator of this scalar is the inner product of U1 with itself. So the inner product, the dot product, in this case, of 3, 4 with 3, 4. So it'd be 3 squared plus 4 squared, 9 plus 16, that's 25. So the scalar is 24 25ths times the vector U1, right, times the vector 3, 4. Which, I guess if you want to put the scalar in, you can. So Y hat, right, the projection of 0, 6 onto this subspace is the vector, 24 25ths times 3. That would be 72 25ths. Right, multiplying 24 25ths by 3. And then 24 25ths times 4 would be 96 25ths. And there's, now I could have just circled this as well. This is totally fine. 24 25ths times the vector 3, 4. But here it is here also when I put the scalar in. Alright. Now let's take a look at a picture of this. Alright. So I'm going to my GeoGebra, right, geogebra.org. Their 2D calculator this time. So remember the subspace was the span of the vector 3, 4. Right? Here's the vector 3, 4. And the span of the vector 3, 4 was this, this green line here. Right? All scalar multiples of 3, 4. Now, here's the vector 0, 6. Right, this blue vector. Now I'm going to put in our projection vector. Right? Remember it was this 24 25ths times the vector 3, 4. So I'm going to call this, V3 here, equals 24/25 times the vector 3, 4, which on my screen here is vector V1. Right. So you see that's in black. Let me remove 3, 4 there. And so what we've got, this is the vector on this line whose end is the closest to the end of vector 0, 6. Remember I said that the vector projection is the closest vector in the subspace to the vector y. So my vector was 0, 6, right, this vector here. Our projection is this black vector onto W. W is the green line, right? W is the span of 3, 4. This vector is the closest vector in W to the vector V2. If you took the distance between them, between these two tips here, that's the shortest distance possible from the tip of 0, 6 to any point on the line on the set W, on the green line. That is the shortest distance from the tip of the blue vector to the green line. And if I drew another vector in here, which I will in a second, right, the vector that I draw from the tip of this vector to that vector, right, should be perpendicular. Right, it should be orthogonal. Right. And let's see. Right, so let me go back to the page. So we found our projection vector. This is the vector in W, right? This belongs to W. This belongs to the span of 3, 4, right? It is a scalar multiple of 3, 4. 24/25 times 3, 4. Now what I want to find is what is a vector in the orthogonal complement of W such that this vector plus this orthogonal complement vector gives me y back, right? So that's the orthogonal decomposition. Find an orthogonal decomposition of y. That means I'm looking to do this. We want to express y as y hat plus z, where y hat belongs to W and z belongs to the orthogonal complement of W, right? So z and y hat should be orthogonal. Their inner product should be 0. Alright, well we already know y, right? That was 0, 6. Right. And we already know y hat, right? We know this projection vector, that was this 24/25 times 3, 4, or 72/25, 96/25. All right, so we know y, so I can use that to find the z, right? We know y is 0, 6. We know that y hat is the 72/25, 96/25, plus, and then to find this z, it's very simple. Again, just subtract. So the vector z here from the orthogonal complement, right, from the orthogonal complement of W, is going to be the vector 0, 6 minus, and then minus that 72/25 and 96/25. Alright, so we're getting, first component negative 72/25, and then 6 is 150/25 minus 96/25 would be positive 54/25. All right. Okay, and let's see how this looks when I go to graph it, right? So I guess also we could simplify this a bit. Both of these have 1/25 in common. In fact, they both have 9/25 in common. So if I pull out the scalar 9/25, then I'd have the vector 9 times negative 8 for the first component. And I'm probably going to get more that I can pull. Yeah, 6 for the second, and these have 2 in common, so I'll pull out 2. This would be 18/25 times the vector negative 4, 3. All right. So what we're seeing here is that 0, 6, right, the original y, right, the vector y is equal to 24/25 times the vector 3, 4. Right, this was that projection vector. Right, this was that y hat. This belongs to w. Right, it's a scalar multiple of 3, 4. That was in w. And then plus, and then this 18/25 times the vector negative 4, 3. And this would belong, this vector belongs to the orthogonal complement of w. And you can double check. Take the inner product of these two vectors. Now the scalars won't matter, so really all you're doing is taking the inner product of 3/4 with negative 4, 3, 4, negative 4, 3. You'd get negative 12 plus 12. That's 0. These are orthogonal vectors, as they should be. So what I have done here is I've taken y, right, the 0, 6, and written it as a sum of two orthogonal vectors, one from my subspace and one from the orthogonal complement of my subspace. And this is the only way that this can be done. This would be a unique representation of 0, 6 written as a vector from w and a vector from the orthogonal complement of w. This is the only way I could do this. Wonderful. And again, let's take a look at a picture. All right, let me put in this vector z, all right, this 18/25 times the vector negative 4, 3. All right, so let me put in another vector here. I'll call it v4. Is 18/25 times the vector negative 4, 3. All right, now it's not, all right, you know, this black one just came up, this v4. Notice, I mean, if I put this, if I put it over here, and if I move this right there, can you see how 0, 6 is the sum of v3 and v4? Right, do you see it? Do you see it when I shoved it? I just shoved it down here to be at the end of the tip of v3. So there's my vector from w. That was the projection vector, v3 here, plus v4 gives me v2, right? This is v2 is the y. This is 0, 6. Right? 0, 6 equals the 24/25 times 3, 4 plus 18/25 times negative 4, 3. All right, there's the y hat plus the z. And you see how they form, they are orthogonal, right? The dot product here, you know, there's the inner product, so orthogonal means perpendicular, and you can see that they definitely meet at a 90-degree angle, these two. Right, maybe I should have moved a little further down. Get to the actual tip of the vector there. There we go. You see how, again, y equals y hat plus z. And it's the sum of two orthogonal vectors. Great. Alright, so we found our projection vector onto w. We found the vector in the orthogonal complement of w. That when added to the vector, the projection vector, gives me y. Right, that's the orthogonal decomposition. Right. Writing any, and you could do this with any vector in R2. You should not just 0, 6. I should have been able to do this with any vector from R2. Take any vector from R2, and you should be able to express it as a vector from the projection a vector from W, which is the projection vector onto W, plus, and then some vector from the orthogonal complement of W. You should be able to do this for any vector from R2. Okay. Alright, so that was an example in R2. Alright, now I'm going to an example in R3, which again we can still picture. I've got the GeoGebra, .org 3D calculator up, so I'll show you that. Alright, so this time W is again just a span of a single vector, so this one's not going to be crazy complicated. But W is the span of the vector 1, 2, 2. So just a line containing the origin in R3. This is a subspace of R3, and once again, the inner product here is the dot product. So that when we say orthogonal, it's perpendicular. All right, so we should be able to take any vector from R3 and write it as a vector from W plus a vector from the orthogonal complement of W. And that's what I'm doing here. So I just picked one, random vector that I made up, from R3. Here's y equals 2, 6, 8. All right, let me show you a picture of what's going on here too. So here's the 3D calculator. Go back to the main screen here. Now the components go in the order of the red, the green, and the blue axes, right? So red, then green, then blue are the order of the components. So here's the vector 1, 2, 2. All right, 1 in the red, 2 in the green, 2 in the blue direction. And you can see the way it's pointing here. Just move this around a bit. All right, so I've got the vector 1, 2, 2. And here's the span of 1, 2, 2, right? That green line that contains every scalar multiple of 1, 2, 2. All right. And the vector we were given, right, was the vector 2, 6, 8. My vector y was 2, 6, 8. Let me zoom this out a bit. That's definitely not in W. All right. Pointing in definitely a different direction. It's not in W, right? It's not a scalar multiple of 1, 2, 2. Okay, so just moving it around here, you can see all sorts of different angles. All right. So again, the green line is W, the subspace, and V2, the blue vector. Zoom out so we can see the whole thing, right? That blue vector is the vector Y. 2, 6, 8. All right, so now I want to find the projection of 2, 6, 8 onto W. So as before, if I want to find this projection onto W, I first need to find an orthogonal basis of W. Find an orthogonal basis of W. Now we have a basis. It's very clear the way I've written it, right? The set with the vector 1, 2, 2 is a basis for W. Right? This is a basis for the vector space W. And just as with the last example, it's only got a single vector in it. So we could declare that it is an orthogonal basis, right? Because there's no pairs of vectors to check. So I guess we could say vacuously that this is an orthogonal basis. So again, this just it's just got a single vector in it. And I mentioned that it's any basis with a single vector we could treat as orthogonal. Okay, and there's only one vector, right? And I'll call that, like I did last time, I'll call this vector u sub 1, right? The single vector in my orthogonal basis. All right, so then this projection vector, y hat, the projection of 2, 6, 8 onto the span of 1, 2, 2 is just the projection of 2, 6, 8, the projection of y onto this vector from this orthogonal basis onto vector u1. And that's it, right? Again, if there were more vectors in the basis, I'd be adding more projections, which I'll do in my final example. I'll have an example where there's more than one vector in the basis. Alright, so again, this is just the inner product of y with u1 divided by the inner product of u1 with u1 times u1. And here the inner product is again the dot product. Just pay attention how the inner product is defined. Alright, so the numerator of the scalar is the inner product of y with u1. So 2, 6, 8 with 1, 2, 2. Alright, 2, 6, 8 with 1, 2, 2. So it's dot product. That'd be 2 times 1 is 2, 6 times 2 is 12, 2 plus 12 is 14, and then 8 times 2 is 16, 14 plus 16 is 30. Right, so I got 30 in the numerator. That's the dot product or inner product of y with u1. And then the denominator of the scalar, the inner product of u1 with itself. So 1, 2, 2 with 1, 2, 2. So it'd be 1 squared plus 2 squared plus 2 squared, 1 plus 4 plus 4. That's 9. Times the vector 1, 2, 2 times u1. Alright, now 30/9 can be reduced, right? Both of those have a common factor of 3. That's 10/3. 10/3 times the vector 1, 2, 2. And there you go. This is our projection of the vector 2, 6, 8 onto the span of 1, 2, 2. This is the projection of y onto w. And if you want to put the scalar in, you could also say that this is equal to, 10/3, 20/3, 20/3. If you put the scalar in. Alright, this is also good. Alright, and let's see this. I'm going to go back to the GeoGebra website here, put in a new vector, which is this 10/3 times the vector 1, 2, 2. Alright, so this is my 6th vector in this picture, so v6 equals 10/3 times the vector 1, 2, 2. Alright, now do you see how that's on the green line? Alright, you see that black vector that showed up? That is on the green line in the same direction as 1, 2, 2, right? It's just a scalar multiple of 1, 2, 2. But it's the vector on the green line whose end, the end of the arrowhead there at the tip, is the closest to the end of the vector 2, 6, 8. If I drew a perpendicular, orthogonal segment from the end of 2, 6, 8 to the end of this vector, that would be the shortest possible distance between the end of the blue vector and the green line. And maybe you can see that it's like directly below, right, perpendicular to the green line there. Alright, so that's going to be one part of the decomposition. Right, I'm going to now I'm going to write the blue vector, I'm going to write 2, 6, 8 as this black vector, right, the 10/3 times 1, 2, 2, the projection, plus some vector that's orthogonal to it, right, some vector from the orthogonal complement of w. Alright, so let's go back and do that now. So again, what I'm asked to do now is let's find an orthogonal decomposition of y, meaning I wish to write y as a vector from w, a vector from the subspace w, that was y hat, that projection vector, plus an orthogonal vector, plus z, where again y hat belongs to w, belongs to the span of 1, 2, 2, and z belongs to the orthogonal complement of w. Alright, well, as before, we already know y, we know y hat, so z, this vector z I'm looking for, is just, y minus y hat. Alright, so it's 268. Alright, y was 268 minus y hat is the 10/3, 20/3, 20/3. And putting those together, right, getting a common denominator. This would be 6/3 minus 10/3, it's -4/3. And then 18/3 minus 20/3 would be -2/3. And this is 24/3 minus 20/3 would be +4/3. Alright, and if we now I can pull out some common factors here. These all have 2/3 in common. Pull out a 2/3 there, or maybe even -2/3 if you want. There'd be -2 there, and -1 there, and +2 there. Alright. So what we're seeing is that y, right, 268. Alright, this was the y, is equal to 10/3 times the vector 1, 2, 2. Alright, this belongs to w. Alright, this belonged to that span of 1, 2, 2. Plus, and then this guy here, 2/3 times the vector -2, -1, 2. Alright, and this vector would belong to the orthogonal complement of w. And you can check that these two vectors are orthogonal. Take the dot product of 1, 2, 2 and -2, -1, 2, right? The scalars won't really matter, remember? That'd be -2 plus -2 is -4 plus 4 is 0. These are orthogonal vectors. So again, when you're asked for orthogonal, an orthogonal decomposition of a vector, you're writing a vector as the sum of two orthogonal vectors, right? A vector from a subspace plus a vector from its orthogonal complement. Alright, and let me put this in. I'll put this vector z in here, this 2/3 times -2, -1, 2. So back to the page, and then we got 2/3 times the vector -2, -1, 2. Alright, and again, maybe you can't see it so hot, but see how these two black vectors are orthogonal. Alright, these two black vectors are orthogonal. And if I put in what's v, one of them was v6. Alright, the projection vectors was called v6 off to the left here. And this vector z, right, the vector in the orthogonal complement, is called v7. And let me just enter what v6 plus v7 is, right? v6 plus v7. See, it's the vector 268. Right, you see the vector 2. See how the black just popped up right on top of 268 there? See, there's the blue, then the black right on top of it. Exactly the same vector. And if I guess I could, it'd be harder. It's hard. I guess you can't really move the vectors around like you could in the 2 dimensions here because there's so many different ways to go. But we can see that 10/3 times 1, 2, 2 plus 2/3 times -2, -1, 2, this projection vector from w plus this vector from the orthogonal complement of w is the vector 268, as we were hoping for. So there's the orthogonal decomposition of 268, right, written as the sum of two orthogonal vectors. Great. Okay. So see, nothing major change there. Same kind of problem. Now so far, my subspace has had a basis with a single vector, right? Has been dimension 1. But obviously that's not always the case, right? You're going to come across examples. You might come across examples with where the subspace has dimension 2, dimension 3, dimension 4, etc. Right? So I've just got one more example here with higher dimensions, and how we go about working with higher dimensions. Right. So same kind of problem, still in R3, so that way I can show you a picture. And then I can show you some pictures in GeoGebra. This time, my subspace is a subspace of R3. W is the span of two independent vectors, the span of 1, 0, 0 and 1, 1, 1. This is a plane in R3, right? Not a line. So W is a plane containing the origin in R3. And once again, this is R3 under the dot product, right? So that way, when I say orthogonal, it means perpendicular as well. Right? All right. And according, what we've been seeing so far is that I should be able to take any vector from R3 and write it as the sum of a vector from W and a vector from the orthogonal complement of W. Right? So I should be able to take any vector from R3 and write it as a vector from W plus an orthogonal vector, right? A vector from the orthogonal complement of W. And it would be the only way I could do it. Remember again that it would be done in a unique way because R3 should be the direct sum of W and its orthogonal complement. Alright, so the vector I've chosen is the vector y is 0, negative 2, 5. Alright, so let me show you a picture of what I've got set up so far. Alright, so let's get rid of all this stuff. From my previous example. Turn all this off. Alright, so we have 1, 0, 0. Let me go back to the main view. So there's 1, 0, 0. See this red vector that just showed up? 1 unit in the red direction, no units in the green direction, no units in the blue direction. There's 1, 0, 0, this red arrowhead here, red vector. And then 1, 1, 1. This green vector that just popped up, that's 1 in the red, 1 in the green, and then 1 in the blue. All right. And then here's the plane that they span. All right, this is W. This is the subspace W. Right? The plane spanned by 1, 0, 0 and 1, 1, 1. Move it around a bit, show you a bit more right there. There's that plane. Okay. Now the vector the vector y I chose is the vector 0, negative 2, 5. This blue vector that just showed up. Now that is not on the plane, clearly, right? 0, negative 2. See, it's definitely not on that plane. It's not on W. So what I'm going to do is find, first the projection onto W. Right? Find what's the vector on this plane whose endpoint is closest to the end of 0, negative 2, 5. Right? Go from the end of 0, negative 2, 5, straight down to the plane here, perpendicular. We're trying to find that vector. Right? And then we'll find the other vector from the orthogonal complement of W that, when added to the projection, gives me the original vector back. All right, we'll do the orthogonal decomposition. All right. So that's the same thing. First part, take this y here, the 0, negative 2, 5, and I want to find the projection of y onto W, right, or this y hat. So first I need to find an orthogonal basis for W. Now in the last two examples that was simple because all my bases, both my bases had a single vector. That is not the case here. I can tell you here's a basis. A basis for W in this example is, clearly the way I've set it up is this set with the two vectors, with the vectors 1, 0, 0 and 1, 1, 1. But this is not orthogonal. It's a basis, sure, it spans the space and these are independent vectors, but these are not, this is not an orthogonal set. Remember, an orthogonal set, it means that every pair of vectors is orthogonal. If you look at the the inner product of 1, 0, 0 with 1, 1, 1, that's not 0, right? It's going to be, the inner product's the dot product here. It's just 1 plus 0 plus 0, that's 1. That's not 0. That's not 0. So this is not an orthogonal basis of W. So what do I do? Well, we've seen this before. It's been a few videos, but if I'm given a basis for some vector space, you can construct an orthogonal basis through that Gram-Schmidt process. So it's not an orthogonal basis for W. So what I'm going to do is I'm going to use what's called, that Gram-Schmidt process, right, to construct an orthogonal basis for W. Alright, so I'm going to call these vectors, say V1 and V2 for, vector 1 and vector 2 here. So 1, 0, 0 is V1 and 1, 1, 1 is V2. Alright, so here's the Gram-Schmidt procedure. And hopefully, again, I'm hoping you're familiar with this, if you've gotten this far. Right. So we're trying to construct an orthogonal basis to W. An orthogonal basis for W. Say, with the vectors U1 and U2, right? Because, it should have two vectors, right? Every basis for a vector space should have the same number of vectors in it. Alright, so remember the first part was simple. I'm just going to have U1 be equal to V1. Alright, just the first vector from my original basis. So this vector in the orthogonal basis is just the first vector from the original basis. So 1, 0, 0. Okay. Alright, then the second vector in the orthogonal basis is going to be the second vector from the original basis minus the projection of that vector onto the first vector in the orthogonal basis, minus the projection of V2 onto U1, right, which is again just 1, 0, 0. Alright, so let's figure this out. Now V2 is 1, 1, 1. 1, 1, 1. Minus, and remember the projection of V2 onto U1. First, the numerator is the inner product of V2 with U1. So what's the inner product of these two? That's just 1. Right, the inner product of 1, 1, 1 with 1, 0, 0. Remember, inner product is dot product here. And then divided by the inner product of U1 with itself, right, U1 with itself. Well, 1, 0, 0 with itself would be 1 again, right, 1 squared plus 0 squared plus 0 squared, and then times U1, times 1, 0, 0. Well, this is simple. This is just 1, 1, 1 minus 1, 1, 0, 1, 0, 0. So that would be, 1 minus 1, that would be 0, 1, 1. So very simple, that one. So here I have found now an orthogonal basis for W, right? Not just any old basis like I had here. So an orthogonal basis for W is the following set. Right, the set with the vectors 1, 0, 0. Right, that was the U1. And the vector 0, 1, 1. Right, that was U2 here, which was V2 minus the projection of V2 onto U1. Right, and you can double check that these are indeed orthogonal now. Right, their dot product is 0. And every vector that's a linear combination of these two is going to be a linear combination of these two, right? We can kind of see that here, right? 0, 1, 1 is a linear combination of 1, 1, 1 and 1, 0, 0. All right, so I'm going to call this, like I said, I'll call this one U1, and the vector 0, 1, 1, calling that U2. All right, so now that I have an orthogonal basis for W for the subspace, now we can find the projection vector, that y hat. So remember, y was 0, negative 2, 5. Y was 0, negative 2, 5. Now I can find the projection of 0, negative 2, 5 onto W using this orthogonal basis. All right, so y hat, I'll write out the formula again. Our y hat is the sum of the projection of y onto these orthogonal basis vectors. So it's the projection of y onto U1 plus the projection of y onto U2. All right. So notice there's more terms this time, right? Again, because my basis had 2 vectors instead of 1, like the first couple of examples. And if there are 3 vectors, then you're going to have a sum of 3 terms, right? The projection of y onto all 3 orthogonal basis vectors. But first you have to make sure that the basis is an orthogonal basis, right? That's the key. All right, and again, writing out the formulas, this would be the inner product of y with U1 divided by the inner product of U1 with U1 times U1 plus, and then the projection of y onto U2 is, the inner product of y with U2, sorry, not y, U2 divided by the inner product of U2 with itself times U2. Okay, and again off to the side, just so I don't have to keep on referring back, remember vector y here was the vector 0, negative 2, 5. Right? The vector 0, negative 2, 5. I'm just going to write it again here so we don't have to keep scrolling back like that. And I've got my orthogonal basis. I've got U1 and U2 right here at the top of the page. All right, so the first part, what is the inner product of y with U1? Now remember, inner product here is again just the dot product. So it's the dot product of 0, negative 2, 5 with 1, 0, 0. That would just be 0. And it would just be 0. And so it really doesn't matter what the denominator is. I mean, the inner product of U1 with U1 is 1 times U1 is 1, 0, 0. But, the numerator is 0. So it doesn't really matter. Plus, this is going to be 0. And then here, the inner product of y with U2, 0, negative 2, 5 with 0, 1, 1. That'd just be 0 minus 2 plus 5, that'd be 3. Alright, divided by the inner product of U2 with itself would be 0 plus 1 plus 1, that's 2, times U2 times 0, 1, 1. Okay, and then putting these together, well, again, this is just nothing. So I'm just getting 3 halves times 0, 1, 1. So the vector 0, 3 halves, 3 halves. All right, there's our projection vector. All right, let's take a look at that. All right, let's take a look at that on the website. All right. So that vector was the vector 0, 3 halves, 3 halves. All right, so I'm going to call this, this is V6. Right. Equals the vector 0, 3 halves. I guess I could just do 3 halves times 0, 1, 1, but I've already started typing it. All right, 0, 3 halves, 3 halves. All right, and look. See that black vector that just showed up? 0, 3 halves, 3 halves. That is on the plane. See, it's on that blue sheet. It's on W. And it's, I don't know if maybe you can figure it from here, but see, it's on the plane, the black vector. And the tip of that black vector should be directly beneath the tip of the blue vector, right? That's the projection of the blue vector. The blue vector is 0, negative 2, 5. It's the projection of 0, negative 2, 5, like straight onto W. All right, and this should be the shortest distance from the tip of the vector 0, 2, negative 2, 5. It should be the shortest distance from the tip of that blue vector to this plane. It would be to the end of that black vector. So I mean, just looking at this, it looks okay. I can't really tell without putting in another vector and adding them. But we have our projection vector. The vector 0, 3 halves, 3 halves. All right. So now, the second part, again, please don't forget you have to have an orthogonal basis for your subspace to do this. All right. And don't forget Graham-Schmidt. All right, so then, as with the other problems, now that I have this projection vector, now that I have y hat, right, the vector on W, now I want the other part of the decomposition of y. I want the vector from the orthogonal complement of W. All right, so find an orthogonal decomposition of y. Break y up. All right, I want to break y up into the sum of y hat plus z, where, you know, again, y hat belongs to W, belongs to that span of 1, 0, 0, and 1, 1, 1, and z belongs to the orthogonal complement of W. So these two will be orthogonal vectors. All right, well, I've already told you we already know y and y hat. All right, we already know y and y hat, so let's find z. Z is y. Y was 0, negative 2, 5. Minus y hat, so minus this 0, 3 halves, 3 halves. And putting those together, we're getting, you know, 0 for the first component. Then this is negative 4 halves, minus 3 halves would be negative 7 halves for the second component. And then 10 halves minus 3 halves would be positive 7 halves for the third component. All right, so there we go. All right, so we have our vector y, right, 0, negative 2, 5, is our projection vector y hat, right? That was the 0, 3 halves, 3 halves. All right, there was a vector from W, plus, and then the vector from the orthogonal complement of W, this z, is 0, negative 7 halves, negative 7 halves, and you can double check. Yeah, and this vector here should be from the orthogonal complement of W. These should be orthogonal vectors if I've done everything correctly, and double check. You know, take the inner product of these two, or the dot product in this case. It'd be 0. Oh, sorry, that's positive 7 halves. Oops, I was like, nah, something's wrong. All right, so positive 7 halves for the third component. It'd be 0 minus 21 fourths plus 21 fourths. That would be 0. All right, again, this is positive 7 halves. Sorry about that. But great, you know, this is called, again, an orthogonal decomposition. I take a vector y, write it as a vector from some subspace. Its projection onto some vector from a subspace, right? Plus a vector from it that subspace's orthogonal complement. Right, I take a vector and write it as a sum of two orthogonal vectors. And let's see it. All right, let's see it. Go back here. That other vector, right, was the vector. I'll call this. You know, this is V7. Was the vector 0, negative 7 halves, positive 7 halves. All right, and maybe you see it, but you see the vector that just showed up, this other black vector, and you see this black vector and the original black vector are orthogonal, right? They're forming a 90-degree angle, and if you were to add them together, you'd get the blue vector. All right, let me zoom this in a bit, and I'll show you. So let me take V6 plus V7 here. All right. V6 plus V7, and see it shows up right on top of, let me turn it off, right on top of the blue vector. See it just replacing the blue vector. It's the same thing. It's the vector 0, negative 2, 5. Right. 0, negative 2, 5 is the sum of these two orthogonal vectors. One from the vector space W, right, the 0, 3 halves, 3 halves, and then the other vector from the orthogonal complement of W, the 0, negative 3 fifths, negative 7 halves, negative 7 halves, right, negative 3.5, positive 3.5. All right. Wonderful. And you should be able to do this no matter what subspace of an inner product space you are given. If you're given a subspace of some inner product space, you should be able to take any vector from that space and write it as a vector from the subspace W plus a vector from the orthogonal complement of W. You should be able to do that no matter what inner product space you're looking at. All right, again, you just have to pay attention to what the space is. You have to pay attention to how the inner product is defined. All right, again, all the examples in this video use the dot product, right? Remember, the inner product is not always the dot product. Just pay attention and be very careful. All right, so I hope that was easy to follow, as easy as it could be. Again, I think the big stuff to take away from this video is on the projections and decompositions. So I'll just refresh your memory. So remember, the orthogonal projection of a vector onto some subspace is the sum of the vector projections of y onto each vector in an orthogonal basis of W. That was the key. All right, you had to find an orthogonal basis of the subspace, and then you could easily find the projection, and here was the formula for that. So remember, if you have an orthogonal basis for a subspace, then the projection of a vector onto that subspace, the y hat, or the projection of y onto W, is the sum of the projections of y onto each orthogonal basis vector. All right. And I think that was the most important stuff. And of course, the last part was, then you should be able to make the orthogonal decomposition of any vector in the inner product space as well, where you take any vector from the inner product space, write it as a vector from the subspace plus a vector from that subspace's orthogonal complement. Right, a projection vector plus, a vector from the orthogonal complement of W. All right. So again, hopefully this was informative and reasonably easy to follow. Of course, I didn't do all possible examples. I just did a few examples from R2 and R3. Of course, you're going to see other vector spaces, other inner products, right? So just pay attention. But the formulas are the same. The procedure is the same. And yeah, so hope you enjoy practicing this stuff. The only way to get better at anything is to practice. And thank you very much for watching.